All right, folks, this is another advanced placement calculus lesson. Hope everybody's doing all right out there. So this is Friday's lesson. The advanced placement people, the squirrels, the College Board should release some more information today concerning your AP exam. We'll see what's what. Okay, but believe it or not, this is the last piece of curriculum that we need to learn, and then we should have plenty of time to review. So we're going to see how things go, and let's get rocking and rolling. So a little star action. We'll start with a little recall. Oh, housekeeping things. Get on my remind, get on my remind, get on my remind. Okay, if there's somebody who's not on my remind that you know of, okay, let them know. Text your friends, spread the word. Hope everybody's okay out there. We do have that assignment that you should have already done. It was due many Mondays ago, all right, before school was postponed. That transcendental functions take-home assignment. Send it to me, okay, via remind or email. That's due on Monday. If I don't get it from you, then I'm going to call the house to see if you guys are okay. Okay, really, we're just doing this to see if we could locate students and see if people are fine. I know some people, I've talked to other teachers, some students have submitted work to them, but they haven't actually joined my remind. If you have a problem with remind, you could always email. So we'll focus on that on Monday, okay, but I want to get some stuff to you. And the third quarter has been expanded, I think, until April 17th, okay? So a couple more assignments I want to get in there so people can boost their grades a little bit. So if you're having issues with stuff, let me know. And let's rock and roll, okay? Something that you actually did a long time ago is if I draw a triangle right here, and then I'll say this is triangle ABC, which I heard is as easy as 1, 2, 3. Now draw another bigger triangle with the same shape. And we'll call this triangle XYZ. Look, and I'm going to tell you right now that these two triangles are similar to one another, okay? So triangle ABC, similar to triangle XYZ. You might be like, where the heck is he going with this? Similar triangles. It's really just for one simple concept. You know, say I know that the side of AB is equal to 3. I know the side of XY is equal to 6. And then I know that AC is equal to, I don't know, maybe 5. And then I want to know what XZ is equal to, okay? And you all know how to do this if you have similar triangles. Remember, corresponding sides of similar triangles are in proportion. You could set up a proportion, 3 over 5 equals 6 over question mark, whatever it is that you want to do. There's easier ways to do it, okay? We should already know that this distance is 10 right here. How'd you know that, Mr. Berto? Great question, Devitt. It was Ryan Devitt. Okay, so let's actually, you know, examine that. If you want to go from 3 to 6, you know that you multiply by 2. And since corresponding sides of similar triangles are in proportion, that means if you want to go from 5 to question mark, you're going to multiply by 2 as well. Okay, you know that 2. That's just the scale factor, okay? You know, so what is XZ equal to? We know that distance is going to be equal to 10 right here. And that's because you have a scale factor of 2. That's what you multiply one side by to get the corresponding side, okay? And they call this thing the scale factor. I don't like the word scale because it, you know, insinuates I'm going to stand on the scale and find out how much I weigh. I don't want to know about that. In calculus, we actually don't really call it the scale factor. We call it the proportionality constant. Proportionality constant. Or the constant of proportionality. It's another way to say it. But the most important thing is that it's a constant. It's a constant. So it's never going to change, okay? It's going to occur for every single side here. And once again, corresponding sides of similar triangles, we say are in proportion, but you could also say they're directly proportional. So let's put a little star here, a little star. Let's say corresponding sides of similar triangles, and instead of saying are in proportion, we're going to say are directly proportional. Directly proportional. And all that means is that you could multiply one side by a constant to create the other. That's all directly proportional means, okay? If two quantities are directly proportional, you can multiply one by a constant to create the other, okay? And we're going to use that concept today. When we talk about the concept, the last thing we talk about in this class, exponential growth and decay. All right, so that's today's lesson right here. You know, as far as the coronavirus is concerned, you probably heard a lot about exponential growth on TV these days, okay? You know, so exponential growth and decay. If you take a look at your dittos, we got a Mr. Martina classic right here. And you guys have seen exponential growth and decay before. You've seen it in math before. You've probably seen it in chemistry class. But there's a specific mathematical relationship when a quantity has an exponential growth or decay. That means that at each instant of time, the rate of change of the quantity is going to be directly proportional to the amount of the quantity present. What does that mean? Okay, well, if the amount of quantity is y, because we don't know what the heck the function is going to represent, might represent, a population, very important thing when you want to talk about exponential growth. Might talk about how much your car is worth. Okay, that's an exponential decay, a depreciation type of thing. But if y represents the quantity, okay, we know it's going to be an exponential growth or decay if the rate of change of that quantity with respect to time, so that's dy over dt, the rate of change of the quantity, is directly proportional to the amount of the quantity present, okay? And the amount of the quantity present is going to be y. Function always represents y values. It's going to tell you that amount. And there's that proportionality constant. Remember, if the rate of change of the quantity is directly proportional to the amount of the quantity, that means you can multiply one of these by some constant to create the other, okay? And this k right here, that's your proportionality constant. If it's positive, okay, that means the rate of change, y is always going to be positive. That's the amount of quantity, so it's always positive. So if k is positive, you could have a positive times a positive. Your rate of change is going to be positive. That's going to be an exponential growth. And if k is negative, you can have a negative times a positive. That's going to be a negative. Your rate of change is going to be negative. That's an exponential decay. You just need to understand on the AP exam, which you might not see on your AP exam because it's going to be shortened, but you'll see this in the future math classes you take. If a quantity is directly proportional to the rate of change of that quantity at any specific instant, that means there's an exponential growth or decay. They'll usually say the rate of change of the quantity is directly proportional to the amount of quantity that's present. And when you see that, that's a differential equation. Okay, that's what we have set up right here. And we're going to separate and integrate and solve this thing. Do the best you can to follow the solving. It's not the worst thing in the world, but you won't really need to solve it because we'll prove a formula here. But remember, separate and integrate. Okay, put that dy on the left-hand side. Then we have ky dt. Some people freak out. They're like, wait, how come it's not like, dy over dx over here? These variables change all the time. Don't worry about that. It could be dA over dt. You'll see problems like that during AP review. Anyway, after you cross multiply, you're not separated yet. This k can stay on the side with the dt. Remember, always leave the left-hand side as clean as possible. But I'll divide by y on both sides. Dictator Grark would divide by y. The rest of us are going to multiply by 1 over y. Okay, and now you're actually separated, and I won't make this y to the negative 1, because if you integrate 1 over y, you should know by now, you get ln absolute value y. Don't worry about the plus c, we put it on this side. Pull that k to the side, he's a constant connected by multiplication. Bring them out. Then multiply by the integral of 1 with respect to t, which is going to be t, plus c. Okay, so we really get ln absolute value y equals kt plus c. And that's a general solution, okay, and it's really in general because I don't know what k is equal to, and I don't have an initial condition to turn this general solution into a particular solution. So I'm actually going to need to solve here. I don't usually like to do this, right? I don't like to, solve for, y until I know what c is equal to, but they didn't give me information here. I'm just proving a formula in general. So if you do want to solve this, you want to make both sides an argument of e, an exponent of e, same thing. We talked about this, okay, we get absolute value of y equal to e to the kt plus c is the same thing as e to the kt times e to the c, right? Okay, multiply like bases, you add exponents. Absolute value y could equal y or negative y, but in this case, y is always going to be positive. That represents the amount of the quantity that's present. You can't say there's, negative 20, COVID-19 infections. That doesn't make any sense, okay? So this is always going to be positive. So the absolute value of y, if y is positive, is y. And check this out. E to the c, e raised to a constant, is just another constant. You can call it anything you want. Some people call it another c. I'll call it a just for the heck of it. And e to the kt times a is a e to the kt. And believe it or not, that's the formula for exponential growth and decay. Okay, there are lots of different ways to write it. What we usually do is you write it this way. Instead of saying y, we say y sub t. People are like, what the hell is y sub t? Oops, I didn't mean to say HE double hockey sticks. What the heck is y sub t? It's early, folks. Can I erase that? Anyway, so here, that y represents the amount of quantity present. Y sub t represents the amount of quantity present at any instantaneous t, after 20 minutes, after, 3 hours, after 10 decades, whatever it happens to be. So this right here is the amount of quantity at time t. So amount of quantity present at time t. You know, and you're always going to be equal to that a right there is, believe it or not, it's just your initial value, okay? So we actually call it y sub 0. It's the amount of quantity that exists at t equals 0, your initial amount, okay? So amount of quantity at t equals 0. You know, if you want to talk about putting money in a bank account, that's an exponential growth, extremely slow one with interest rates these days, and they're probably going to get worse. But anyway, this would be your principal, the amount you initially invest. Okay, so the amount of the quantity that exists, you know, your initial amount, you could say it that way if you want to. It doesn't always actually need to be the amount at t equals 0. It's just an initial starting amount, but usually that's what they put here. E is a constant, k is the proportionality constant, and t is just time, okay? So this k right here is the proportionality constant. Proportionality constant. And t is just going to represent time. The proportionality constant is really cool because that exists to be the exact same thing at any time t, okay? So, you know, they might actually tell you the amount of quantity that's present at one time t, and then tell you the amount of quantity that's present at another time t, and that'll allow you to solve for k, which will be able to give you the amount of quantity at any time t, okay? So y sub 0 is going to be replaced, and k is going to be replaced, and then that's really your exponential growth or decay formula, okay? You probably want to memorize this thing right here. Whenever they tell you that the rate at which a quantity changes is directly proportional to the amount of the quantity present, that's this formula right here. You don't need to set up the differential equation and solve it every single time. But you use this so often, it's got to be kind of cool to actually see, you know, where this stuff comes from. So let's do this. Let's go to the back of the ditto. Turn the sheet around. Turn it round and round. And let's try example 1. These problems actually really aren't too terrible, okay? And they're very antiquated. You don't really see a lot like this on the AP exam these days, okay? But we'll go through it anyway. You may have solved problems like this before. A bacterial culture, initially has 400 bacteria. That's our initial amount, right? The amount of bacteria at t equals 0. And is growing at a rate directly proportional to its size. Remember, if the rate of change of a quantity is directly proportional to the amount of quantity present, the size, that makes it an exponential growth. Exponential growth. You don't need to set up that differential equation. Sometimes you will, believe it or not, with different types of problems we'll get to in a minute. But that means that, look, you know, y sub t is going to be equal to y sub 0 e to the kt. And they're telling you that if after 5 hours, there are 10,000 bacteria, so they kind of gave you another initial condition there, then at what time, so at what time t, will the number of bacteria be 20,000? So if you want to know when the number of bacteria is going to be 20,000, that's this guy over here, 20,000, the amount of quantity present at any time t. What time t? I don't know. That's what I want to find out. Y sub 0, the amount of the bacteria at t equals 0, that's 400, yo. There's also a calculator problem in case you didn't notice. E is a constant. Here's the problem. They didn't tell me what k was, and t is what I want, right? I actually want to solve for t. So the only issue here that I can't solve for t is that I don't know what k is equal to, but that's the proportionality constant, okay? He's going to be equal to the same thing at any given instant of time, and they gave me information. They said after 5 hours, there's 10,000 bacteria. So you could actually set up this formula again and say, okay, the bacteria amount is 10,000. The initial amount still 400. E to the, I don't know k, but now I know that t is equal to 5 because they told me after 5 hours, okay? This would be the amount. And that actually gives us an equation that we could solve for k. And then we could take that k, plug it right in here, and then solve for t, okay? It's the proportionality constant. It's going to work at this instant of time, just like it works at the instant when t is equal to 5. It is a calculator problem, but we'll try to avoid it as much as we can because things like this can get a little wonky the way you have it set up. Dividing by 400 on both sides shouldn't be an issue, okay? We get 100 equal to e to the 5k. More practice, you know, solving over here. Is it 100? Why do I feel like that's wrong? 10,400. Oh, so I just canceled these out and then didn't even do 100 divided by 4. Yep, like I said, it's real early. Anyway, so that's a 25, I think. Check my work. If I'm making mistakes on these videos, let me know, okay? Not so easy to do this. Doing the best we can, just like everybody else. Let's eliminate that e. Let's make both sides the argument of ln. You want to get some colors going on? The colors, children, the colors. All right, so the ln of 25, what is that, 25 or something, equal to the ln of e to the 5k. So ln 25, I'll leave it that way. You can make it the ln of 5 squared. You can make it 2 ln 5. Do we want to get that crazy? Maybe we do. Why not, right? Let's make it the ln of 5 squared. You have the calculator anyway. The problem is these are nasty irrational values, okay? So you can't really round them, and that'll cause some issues if you do start rounding. So I'll do this. This is really 2 ln 5 equal to 5k. Now I could divide by 5 on both sides, and I get 2/5 ln 5 is equal to k. That's our proportionality constant. That works at any instant of time, okay? So now I could take that and plug it into this formula over here. So now my k is 2/5 ln 5 times t, right? You all see what I did there. And then look, to solve, divide by 400 on both sides. Let's make sure we do 200 divided by 4 this time to get the 50. Actually, 50, excuse me. Okay, and here we get e to the, believe it or not, if you want to write this appropriately, you know, 2/5 ln 5 times t, people usually write 2/5 t ln 5. Okay, so that's really the same thing as this right here. You don't technically need to do it, but you should be able to recognize it, okay? Now we'll make both sides the argument of ln. No fancy colors here. Okay, and now we get ln of 50 is equal to 2/5 t ln 5. And at this point, let's go for the calculator, okay? So think about what we're going to do. We're going to divide by 2/5, and we're going to divide by ln 5. All right, so let's get a good old Calci going on. How you doing, Calci? What up? Okay, so here we have, we'll even start with the ln 50. By the way, if you want to divide by 2/5, that's fine, okay? But only Sabrina is going to be dividing by 2/5. The rest of us are going to multiply by 5/2. Little alpha y equals for shequies, you got it. Okay, so multiply by 5/2. And then don't forget that now I need to divide by ln 5, then divide by the ln of 5. Okay, and you can see that my answer is approximately 6.077, okay, if you're a rounder. Okay, remember, if you put 6.076, you're not wrong, but you're a lousy stinking truncator, okay, and you'll always be that way. Anyway, just kidding around. You can see here, they actually round to the nearest tenth anyway, okay, so here we get 6.1 hours. Okay, so not as bad of a problem as you might think. Really these problems consist of, they want to know something at one given instant, but you need to figure out what the k is, and they'll give you information about another given instant to solve for k. And I don't even think you'll see those types of problems on the AP. Certainly not this year. Even in the past, they're kind of outdated, but there is one specific type of problem. Let's do example 2 first. It's actually a little bit quicker. It doesn't say whether you could use a calculator here or not. Let's do it without the calculator. I don't even know if it says no calc, but let's try to not use the calculator. And then if we get stuck, we'll use it. The radioactive element, carbon-14, has a half-life of 5,750 years. You're not really responsible to know what half-life means on the AP exam, but most of you have taken chemistry and you know about it. Carbon-14 decays predictively, okay, which is why they actually use it for dating. The radioactive element carbon-14 has a half-life of 5,750 years. That means whatever amount of carbon-14 you start with, if you wait 5,750 years, there will only be half of it left, okay? You might have to, pass that research down to someone. It'll take a while for you to figure that out, but, this is a true thing right here. So then they tell you that its rate of decay is directly proportional to the amount of carbon-14 present. And remember, if the rate at which a quantity changes is directly proportional to the amount of that quantity at any given time t, that means that it's an exponential growth or decay situation. If it is exponential growth, what are we really talking about? This one that we're doing is decay, but the one we did previously was growth. It just means that at any specific time t, right, if you want to pick this t value right here, maybe t sub 1, the rate of change of the quantity at that instant, which, by the way, is the slope at that instant, the slope of the tangent line, the slope of the tangent line, the derivative, okay, where is it? Whoop, there it is, all right, is going to be directly proportional to the amount of the quantity present. So the slope of this line right here, you could actually multiply it by some constant to get this y value right there. And you could always do that, at any other time t, maybe t sub 2 over here, which obviously corresponds to y sub 2, this value. Okay, if you take the slope of this tangent line, and you multiply it by the same k you got over here, it's going to give you that amount right there, y sub 2. So that's what's really going on with an exponential growth or decay. This one right here, you know, we got y sub t equals y sub 0. I mean, y naught e to the kt. It's a physics joke. You know, and now, you know, what do they tell us? Well, we want to know if there's 100 grams present of carbon-14 initially, how much would be left after 1,000 years? So now we actually want y sub 1,000, right? You know, actually, we want the quantity after 1,000 years. We know the quantity after 0 years, the initial amount is 100 grams. Then we got e to the k, and then you want to know how much would be left after 1,000 years. So I know t this time is equal to 1,000. You know, and the problem here is that, well, now you need to know what k is equal to, okay? And the good thing is they told you something else. They told you about the half-life. So we know if you start with 100 grams of carbon-14, after 5,750 years, you're going to be able to know that this will decay by a half. It'll be equal to 50. Okay, so that's what we're going to use right here. If you divide by 100 on both sides, you get 1 half equals e to the 5750k. Now we could solve for k. This is kind of cool because you could have started right here. Technically, this is still an initial amount. It's equal to 1. Half of 1 would be a half, okay? So you could always do something like that if you want to. It'll always simplify down to that. You know, anyway, so now we want to e both sides, not e both sides, pardon me, take the ln of both sides. So ln of 1 half equals the ln of e to the 5750k. ln of 1 half is really ln1 minus ln2. They never write really ln of a fraction. They like to break it into subtraction. That equals 5750k. And this is really 0 minus ln2. Okay, so 0 minus ln2, negative ln2, equal to 5750k. And now I know what my k is equal to. Negative ln2 divided by 5750. That's what k is actually going to be equal to right there, okay? And now you could plug that back into the original. So if you want to know the amount of the quantity at 1,000, after 1,000 years, 100 e to the negative ln2 over 5750 times 1,000, okay? And look, you could technically leave it there. That's the answer. But let's go calculator here. I don't know if on the ditto it says to use a calculator or not. Obviously, it doesn't because I'm using the ditto right here. But you could do this to make things a little bit easier because plugging that in, getting an answer, not the easiest thing in the world. So maybe this, maybe a little alpha y equals for shequies. Maybe put k in the calculator. So negative ln2 divided by 5750. And I'll store that answer in. Why not for k? I mean, you could use any letter that you want, but I'm going to use k, okay? Pretty small number here, a negative number. That's why it's an exponential decay. And now when I plug in here, you don't have to write it this way. You could just write 100e to the 1,000 times k, 1,000k. Okay, whatever your kiss begins with. And I get approximately, so the amount of quantity that's going to be present after 1,000 years is approximately, I get 88.644 units. I need units. Did I write units here? This would be grams, right? Because it's an amount. Wow, am I really slacking? Did I not write units on the previous problem? Oh, it was in the answers. Okay, it was hours right there. So that should be all right. You know, these types of problems really aren't that bad. And like I said, they're kind of antiquated. The problem that you will see on your AP exam without a shadow of a doubt, well, you would if it wasn't a shortened AP exam. More information on that today. Like I told you, I'll get on top of that. Don't worry. If you take a look at number 7. Okay, number 7 right here. It's actually not exponential growth and decay because now it says a differential equation describing the relationship that the rate of change of the velocity of a particle at any time t is directly proportional, you can multiply it by a constant, to create the square of the velocity. And that's not exponential growth or decay. It would be exponential growth or decay if it said the rate of change of the velocity of the particle at any time t is directly proportional to the actual velocity of the particle. That's not true here. But remember, when two quantities are directly proportional, you can multiply one by a constant to create the other. Very popular part 1 problem on the AP exam. Who knows? They might give you like a free response that has like a bunch of part 1 problems in there. I don't know. So the rate of change of the velocity of a particle at any time t, so that's the rate at which v is changing with respect to time, that's dv over dt. They tell you is directly proportional, which means you can multiply by a constant to get the square of the velocity, and the square of the velocity is velocity squared. So really, if dv over dt is directly proportional to v squared, you can multiply 1 by a constant to get the other. And I've always seen that they multiply the constant by the amount, or, you know, the amount squared, the square root of the amount, whatever it happens to be. They don't usually multiply the rate by a constant, but you could do it that way as well. Anyway, we can see our answer here would be C. Okay, so this is the type of problem pretty popular on the advanced placement exam. And you'll see it on the take-home as well, okay? You know, you will be getting some more take-homes. We got that one take-home that I want on Monday if possible. There's a slope fields take-home, and then we're going to do a take-home quest on this stuff, okay? I'm trying not to put it all out to you too quickly. I know this first week is kind of like a readjustment. But like I said, get on my remind, and we'll get you where you need to be. Hope these videos are okay, okay? You know, send me an email or send me a text to remind, whatever. You know, if you think something's working out, if you think something's not working out, you know, let me know. We'll do the best we can. You know, I hope you guys are all safe and happy and healthy. And I'll see you on Monday for the last lesson of the curriculum, technically, before we go into review on Tuesday, even though it's really just kind of a review of what we've been doing, obviously. Anyway, this is Bertos signing out, and take it easy. Adios.